While we're getting started, so I have kind of two hats. So I'm a student and a PhD student and a fellow at the Colorado School of Mines. And in that, I research space resources and also space nuclear. And then I am also the regulatory director at Xenopower, which is a space nuclear startup. So early in my research, I was surveying all of the possible intersections between space and nuclear and how the space sector might help the nuclear energy sector. And I came across this really dumb idea, which is launching nuclear waste into space. Obviously, I wrote about that and said that was a dumb idea. Now I'm at Xenopower, and what we do is we take nuclear waste and we package it, and then we launch it into space for useful purposes. And I'm also the one that's responsible for figuring out how to convince the government that we can do that. So I'm really excited to talk to you all about space nuclear technologies today, both radioisotope power, which is the historic space nuclear workhorse, as well as fission power systems, because we're really at the early stages of commercial space ethos going into the nuclear sector broadly, but also for commercial space nuclear. So the easiest way to think about space nuclear is there's two sets. There's radioisotopes, which are essentially nuclear waste products that you package. You have watts to maybe low kilowatts electric thermal, and you can do that distributed for all sorts of applications. The Apollo missions use them for surviving the lunar night. Mars rovers use them to make sure they can operate with dust storms. You have them for deep space probes like the Voyager and New Horizons missions. And then we have fission reactors, which really is kind of, again, a U that if you're talking really small radioisotopes, if you're getting up to dozens of kilowatts, but really starting to get to megawatts, that makes sense for fission surface power on a planetary surface or fission reactors for propulsion. So why is there a big moment in space nuclear technologies right now? It's really because we are heading to deep space celestial bodies, and nuclear has significant advantages there, both to help us when we don't have sun or to complement sun-centric architectures. So on the Moon and Mars objectives, the #1 lunar infrastructure objective, the #2 #1 Mars infrastructure objective are power systems to make sure that we can have a sustained presence. Radioisotopes and fission surface power help both of those. Recently, STMD released the civil space shortfall ranking. They surveyed the entire civil space sector to figure out what are our technology priorities that we should be focusing on in the next several years. And if you actually look at the 187 things that they looked at, nuclear technology is ranked very highly across those. Survive and operate through the lunar night. There are other potential technologies. Radioisotopes are the only thing that are proven to do that repeatedly and sustainably and well. But then we have high power energy generation, so fission surface power for Mars and from the Moon. So this is definitely something that's starting to be prioritized. And the big change we're starting to see is that we're actually seeing missions getting manifested at a pace that we haven't seen before. So for the last several decades, since the end of the Cold War, we do about one radioisotope mission per decade. That's changed. On the left, you see the Dragonfly quadcopter that's going to go to Titan and explore the Titan surface. It's going to cover more ground than any other planetary exploration system in history. That's using a traditional plutonium-based radioisotope system that NASA normally has. But then in the middle, you see the Rosalind Franklin rover, a European Space Agency rover in partnership with NASA. It's using plutonium heater units, but it's also using an americium heater unit, which is a prototype for a European initiative to develop new types of radioisotope technologies. And then on the right, you see Draco, which is a DARPA and NASA collaboration to create a nuclear thermal rocket. This would be the first fission reactor that the US has launched in space in 60 years. It would potentially set up a whole new, much more efficient way to travel in cislunar space for Defense Department purposes, but also to potentially bring astronauts to Mars. All of these are coming. These are manifested missions. They actually might be launching in a period of about 12 months, which is kind of crazy. I don't know if the Cape is ready for that. But it's really the first part of a broader wave. So we have a number of projects that we're developing right now across the entire sector. Xeno is definitely leading on the radioisotope side. But the big change here is that just like we've seen with commercial space launch, other elements of the commercial space sector, the government is turning to the commercial sector to develop these new technologies. We have about $700 million that has been granted across Draco and a bunch of other projects to different commercial companies. A lot of these commercial companies are terrestrial innovators because of advanced reactor technology on Earth. They're focusing on climate mitigation. But we also are seeing about $500 million that could be another award coming up in the next year of appropriations. This is a lot of money. So on the far left, you see an example of one of the Xenopower projects. We're working on radioisotope electric propulsion for the Space Force, a lunar surface power system to help you survive and operate through the lunar night with NASA. And we're also doing a purely commercial project to provide heater units for all the lunar landers that are heading so they can actually survive through the lunar night. In the middle, you have fission surface power to actually build a 40 kilowatt electric reactor on the lunar surface. That's heading to flight, and that would actually be nominally paired with the first ISRU pilot plant on the lunar surface. And the right side, you have nuclear electric propulsion, which is it's called JETSON, great name, project that the Air Force Research Lab is looking at, again, to develop things in cislunar space. So one of the big changes that's happened that is enabling for this is because of the terrestrial innovations and other things, we've actually secured the nuclear supply chain, which is one of the biggest barriers to developing advanced nuclear technologies. On Zeno's part, on the left, you actually see we are recycling an old strontium-90 generator, and we're using that to actually develop our first power system, so we've got fuel. On the right, we've actually secured a partnership to start fabricating those systems, so we're going to be fabricating our first heat sources in 2026. But more broadly across the nuclear industry, we're seeing a lot of supply chain development, again, to meet the demands of climate change and develop advanced reactor technologies. On the bottom, you see a Centrus facility that's developing what we call high-assay, low-enriched uranium enrichment. So typically, when we're talking about power plants, you have low-enriched uranium. But because we're looking at new technologies, you get to a high level of about 20% enrichment. This actually allows you to have commercial companies developing space reactors for the first time. That's what's underlying all these new initiatives on the government side. The regulatory pathway, everyone is going to say, hey, nuclear, there's a lot of regulatory issues. We've had major advancements here. There was a series of executive orders in 2019 and 2020. We now have a very straightforward performance-based system so that if I build a system for NASA, I actually can use all of the same safety analysis and regulatory requirements to fly that same system with the Defense Department or fly it commercially. The NEPA burden, we used to have to do environmental impact statements for all space nuclear missions. The 3 missions I mentioned earlier all did environmental assessments in less than 12 months. They blew their schedules out of the water. They got no opposition. We have some outstanding issues, especially related to how we do in-space things, but this is ready now. We can do the first missions. And this gets to kind of, I think, the big summary of where we are right now is that we are on the pathway to commercialization. So Zeno, we actually went ahead and did our prototype system, an actual nuclear heat source we developed last year and demonstrated at National Lab. In the middle on the fission side, you can actually see a small reactor the Department of Energy developed in 2018 and actually demonstrated. That's called kilopower. And that's leading to what we call Gen 0 now, where we're essentially developing flight-capable systems to be able to allow us to prove out how we go through all the process, actually operate in space, and then getting to Gen 1 and Gen 2 systems by 2030 and into the 2040s that allow us to do all sorts of activities. Ubiquitous radioisotope across all of the lunar surface, fission surface power for all sorts of bases or high-energy applications on the Moon and Mars surfaces. And if you're looking at any sort of Martian exploration, the ability to take astronauts, send them there in a way that's going to be a lot faster, which means a lot safer for the astronauts involved. So thank you. I'm happy to kind of talk about any of the questions you might have.
Cool. I'm going to start on this side of the room now.
Thank you. Can you use these and apply these to power generation on Earth, or is there something that makes it, if not easier, but just a better idea to do these in space first?
Yeah, so for radioisotope systems, we actually did a lot of systems terrestrially during the Cold War, primarily for government applications, and that's actually where a lot of Zeno's work is focuses on terrestrial applications, so that really helps on the business case side. More broadly for reactors, especially when we're talking about HALEU and advanced reactors, there's a big focus on developing what we call microreactors that allow you to have distributed nuclear energy. And those are like in a container size thing that are maybe a megawatt to 10 megawatts. And that's what's actually leading to a lot of the corporate interest in supplying these as space reactors. They're basically developing the technology to build that on Earth, and they just want to do a little bit more to develop it into space.
Oh, yeah, Tiffany, go for it.
This is probably a dumb question, but picture 100 years in the future, people living on Mars, sustained human settlements. Aren't they going to be critically reliant still on Earth for their power needs if nuclear is the main route for this?
Great question. So as far as we know right now, there are not established Martian thorium or uranium resources at a significant degree. What you would probably see is that I would imagine you'd have some level of significant Mars and Earth trade, and you'd have the most high value mass that would be doing that. And so you would be looking at fabricated fuel, which is the hardest part of a nuclear system. Everything else you can manufacture in situ, but unless you actually have that, you would still need the supply chain. And I would add the addendum there, which is a big policy consideration, is you would probably want to do a lot of recycling on the Martian surface of your nuclear fuel. And that raises all sorts of weapons considerations. And so that would be a really big policy concern when we get there.
Okay. Thank you so much.
Thanks.